Hello everyone. Today I'm going to go ahead and finish up chapter 40. I'm going to make it about 25-ish minutes like I did yesterday. And I want to just focus on what are population ecologists going to study and be interested in. And yesterday I talked about how density and dispersion are something that they're going to want to study. And the way to determine population size and density, there's three methods. This one, counting every individual, not likely going to happen. Random sampling is okay, but the mark recapture method, remember when I talked about the roaches, and if you marked the backs of all the roaches and then let them go and then took another sample and you plugged it into a math formula, you can pretty much figure out what the population size is. Patterns of dispersal is something that ecologists are going to be interested in. In particular, I can think of an example of the reason why this would be important is if they want to build, let's say, a research building. Going to want to know the pattern of dispersal of different organisms so you don't plop a building right on top of them. All right, demography. So ecologists are going to want to study statistics that affect population size. And the reason why they're going to want to do this is so the populations of different animals and plants can be monitored. So if something starts to go wrong, interventions can be made early on. So an example would be if it's noticed early on that the population size of a certain animal is declining rapidly and it's not part of their usual survivorship, then maybe a sanctuary or something like that can be built to try to make up for whatever it is that's going wrong. All right. Additions occur through birth and subtractions occur through death. I think that's pretty obvious. What can be built from charting births and deaths of certain animals is called a life table. And this is going to be a summary of the survival pattern. And so what you can do from a life table is figure out what type of survivorship does this animal belong in. And so if we just look at this table right here, this data table, this is for ground squirrels, and we have it divided into females and to males. And then if you look over here, these are the ages. And then they're going to divide it up into the number that are alive at the beginning of the year, number of deaths during the year, death rate. And so what you can notice on the death rate is if you look between the ages of 0 and 7, the death rate of squirrels actually appears pretty constant, it seems like. You can also notice from here that females are more likely to survive a little bit longer than males. So what we can do with that is make what's called a survivorship curve. And so I want to start with type 1. Type 1 is where humans would fit in. Humans are going to have a really low death rate in early age, and then the death rate is going to drastically increase in old age. So we are of a type 1 survivorship. Type 2 is that there's a constant death rate over the lifespan, as we saw with the squirrel. And then type 3 is that there's a high death rate in early age, right? And we have these oysters right here, and mollusks would fit in that too. Mollusks and oysters would fit into type 3 survivorship. The one thing I think is important to know is if an animal is of a type 1 survivorship, they're usually not going to have very many offspring. And the reason they're not going to have very many offspring is that the likelihood that their 1 or 2 or 3 offspring are going to survive is actually pretty high. If an animal is of type 3 survivorship, they are going to have a lot of offspring. And the reason for that is because the survival rate of their offspring is going to be low, so they need to make up for that by having a lot of them. All right, so the question, each female fish produces millions of eggs per year. Draw and label a survivorship curve for the fish. All right, and so like I said before, if they're going to have a ton of offspring, they have evolved to do that. That's because fish are a type 3 survivorship. All right, so right here, this is going to be a change in a population size during a time interval. So I wouldn't get caught up in this. This is just one unit right here. It's the change in the population size during a time interval. And the way that that is determined is pretty obvious, is births minus deaths, where N equals population size and T equals time, B equals births, D equals death. And so that's a pretty easy way of determining how did the population size change over a certain time period. So if you start with 1,000 people and you have 100 births and 50 deaths, how did it change? Well, you would do 100 minus 50 equals 50, and then add that to the original population size so that you now have 1,050. So something that most demographists would be interested in is the population growth of humans in different countries and how that has an effect on that country. So here you see a table where it shows that the number of births is somewhat equal to the number of deaths. So when you have zero population growth, there are some benefits and some negative aspects to it. So countries like Russia, Romania, Japan, Poland, Austria, and Italy, and Greece, and among many others, tend to oscillate between zero population growth and actually negative population growth. And so what demographists we'll look at is what is the benefit of this. So to have a low population growth or zero or negative could potentially help by raising wages and reducing government spending on the needy. The downside of this is that if the population growth becomes too negative, then there can be economic issues, and I'm not an economics teacher, but I can imagine that if you aren't replacing your people in the economy, things can get a lot worse. So that is something that's kind of interesting that kind of bleeds into economics. All right, we have two types of population growth models. One of them is called exponential, and one of them is called logistic. And so with exponential growth, there are ideal conditions, and the most important thing to know about this is that the population grows rapidly because resources are unlimited. And the example is when African elephants are put in these sanctuary areas where resources, they keep their population down low, or their population naturally is low, at least to start out with. They're not reaching any kind of capacity, and resources are unlimited. That is exponential growth. So it's a J-shaped graph. And so if a ecologist was doing a study on the population growth to see if they are exponential or if they are logistic, or where they are in that certain time period, they'll use this formula right here. So remember, dn over dt, this is number, this is time, over a certain time period, how much is the population growing? And so all you would do is take the growth rate, multiply it by the original population size. That will tell you how much more is being added. And so let me give you a sample problem. So this problem says, it's going to tell you that it's exponential growth, and you're going to know it's exponential growth because it doesn't say anything about the population having a capacity. So it says a certain population of mice is growing exponentially, so you know there's no capacity. The growth rate is 1.3, and the current size is 2,500. How many mice are added to the population each year? So what you're doing here is you're literally just plugging 1.3 in for R, 2,500 in for N, and I didn't give the answer, but I can. I have my calculator right in front of me. So 2,500 times 1.3. It looks like that population is growing by 3,250. So if you wanted to know in the first year what the total population size would be, you would then add that to the original. right? In 2009, sorry, this is an old statistic. In 2009, the United States had a population of about 307 million. If there were 14 births and 8 deaths per 1,000 people, what was the country's net population growth that year? So the United States is considered to be at exponential growth, where we don't have a capacity yet, or we don't know what that capacity is going to be, or we're not reaching it just quite yet. I think that's a debatable topic, but for our purpose, we're just going to pretend that we are exponentially growing. And so you'll notice that this problem right here is giving you N. It's giving you the original population size. It is not giving you R. But you notice there's birth, death per 1,000. So you can calculate a growth rate. 14 minus 8 divided by 1,000. And so that'll give you an R of 0.006 for this problem. So if you want to know how many more people were added, you would just do 0.006 times 307 million. And you would get 1,842,000 added. So I know some of you are probably sitting here a little bit frustrated because you're like, can you please work out the problem for me? I do not have the ability to actually work it out here, but if you want some extra help with it, please email me and let me know. But hopefully you just see that with exponential growth, you're going to use this formula right here. You're going to figure out how much more is added to the population over that time period. You're going to find a rate of growth, and you're going to multiply it by the original population size. And so this just tells you a rate of growth. Well, if you have 14 births and 8 deaths, the growth would be 14 minus 8, which would be 6, and then you divide it by 1,000 to get a rate. And then you just multiply that number, 0.006, times 307 million. That tells you how many more were added. All right. Unlimited resources are very rare. So what you're going to see is the exponential all right, so that was exponential growth. Realistically, unlimited resources are rare. So the more realistic growth model is called a logistic model, and it's going to incorporate something called carrying capacity. Carrying capacity means this is the maximum amount, the maximum size of the population that can be sustained by the environment because resources are limited to a certain extent. And then this is just giving you some examples of paramecium population. About at this point, food's going to run out. The environment's not going to be able to support any more than this amount. And this is giving you Daphnia. Daphnia are kind of like, they're similar to brine shrimp. They look similar to brine shrimp. At a certain point in time, they will not be able to be, the population size won't be able to support. So you reach this thing called carrying capacity. And so the letter that we designate for carrying capacity is K. So if you're given a problem with logistic growth, here is the formula. And so dn over dt, once again, is just the change in population, whether it's growing or it's getting smaller. R, again, is still the growth rate. N is the population size. You're just adding a new letter in called carrying capacity, and that's going to be given to you. And you just plug in to find out how many more are being added over that time period. All right. So here we have a problem. Right, so this problem right here will tell you that the population has a carrying capacity, so therefore you know you're going to use the logistic growth formula. So it has a carrying capacity of 900. It gives you R. It gives you N. All you do is just plug in to this formula right here. And if you want to pause, go ahead and pause now so you can do that. All right, so then once you work out this problem, you should get I would round to the nearest whole number. You should get 247 being added to the population over that time period. So pretty easy problems. You just plug into a formula. All right, life history. So kind of moving on to the next topic here. We're just jumping around to all the different things that these population ecologists are going to study. A life history is the traits that affect an organism's schedule of reproduction and survival. So there's 3 variables that are going to affect that: the age at sexual maturation, how often the organism reproduces, and the number of offspring during each event. So that will give a really good life history of the reproduction and survival. So these traits are evolutionary outcomes, not conscious decisions by the organisms. So natural selection has selected for individuals that have a very particular 3 variables that have to do with their schedule of reproduction, because that is what was most conducive to the survival of that organism. So here's a really interesting example. The average rabbit reaches sexual maturity at 3 to 8 months old. It's pretty early. They have the rest of their 9 to 12 plus years to get it on, sorry for lack of better wording, through egg sperm production. Their breeding season lasts 3/4 of the year and they don't have heat cycles. So this is what's really interesting. I'll just paraphrase this. When 2 rabbits copulate or have intercourse, it induces the female rabbit to ovulate. So what we know about humans is that females are going to have a scheduled ovulation no matter what. So human females are going to ovulate on day 13 or 14 of their cycle every month, no matter what. Basically a normal female that doesn't have any medical conditions. But rabbits, this is very convenient, this is very efficient, that they will not ovulate unless they've had intercourse, which is kind of cool. So it says after 40 seconds of magic, the egg is emitted for fertilization. Rabbits gestate for only 30 days, so they're only pregnant for 30 days, and they'll have a litter of 4 to 12 babies, depending on the breed. And once the babies are born, the doe can mate and get pregnant again as soon as the following day, it says. So it says that it reaches maturation of 3 to 8 months old. I did find that some of them can mate the following day. I would actually need to fact check this. But anyways, it looks like they can make large litters. So this would be the reproductive schedule of a rabbit. All right, the reproductive schedule of an agave plant is something called Big Bang reproduction. They produce many offspring at once, and the individual often dies afterwards. The reason that the individual dies afterwards is because it takes so much energy to reproduce, and so basically they're like sacrificing themselves, and because of the energy put forward, they can produce a lot of offspring, but then afterwards they just can't survive. So this is what the agave plant does, and they live in a less stable environment, so that's why this is very convenient and beneficial for the agave plant, because producing many offspring, a lot of them might not survive, and so that ensures that genetics will be passed on the more offspring that they produce. Heteroparity is a type of reproduction where there's repeated reproduction, few but large offspring, and there's a more stable environment. So because there's a more stable environment, I'm thinking of that type 1 survivorship. They don't need to make very many offspring because there's a strong likelihood that they are going to survive. All right, we have K-selected populations and R-selected populations. K-selected populations are going to live around carrying capacity. They will have high prenatal care, low birth numbers, good survival of young, and it's density dependent. So K-selected means living around carrying capacity. So remember I said some people think that we are reaching a carrying capacity, that we know what that is. Some people think that we are in an exponential growth and we don't. know what that carrying capacity is going to be. Either way, though, animals that are like humans are going to live around carrying capacity because we pretty much are reaching that point, getting up there. High prenatal care, low number of births, good survival of young. Density dependent means the more humans there are, the more likely they're not going to reproduce as much. So think of it as if your parents had 2 kids, they decided that's enough. Density dependent. There was enough offspring, they recognize it, so they're going to stop reproducing. Our selection is mostly for those animals that are in exponential growth. There's little or no care for young. There's high birth numbers, poor survival of young. It is density independent, and fish and cockroaches would belong here. So think of case selection as being iteroparity, type 1 survivorship. So iteroparity, type 1 survivorship. Our selection would be something like, kind of like similarity and type 3 survivorship. So this is just categorizing the reproductive tendencies of different types of populations, really. All right. So factors that are going to limit population growth are density dependent factors. So something that can limit a population from growing would be predation, disease, competition, waste accumulation, and physiologic factors. So those are density dependent factors. Density independent factors means that it doesn't matter how large the population is, the population size could be limited by things like natural disasters. So basically density independent factors are the things that natural disasters really are the only thing that fits under that. That is going to affect the size of a population regardless of what the size of the population was to begin with. So here, if you look at density dependent, predation, well, the way it affects the size of the population is going to have to do with what the size of the population was to begin with. The larger the population size, the more likely they're going to suffer the effects of a predator because they're more able to be seen. Same with disease, and that kind of brings us to the idea of what we're doing right now. The more people are congregating together in a large, dense number, the more likely that disease is going to spread. So that can, the size of the population to begin with is going to really determine how each of these factors is going to affect it. So hopefully that made sense. All right. I want to talk about boom and bust cycles. So what can affect the population of one organism? Well, it will be the population of another organism. So if you look here is a lynx, that is chasing a hare, the snowshoe hare, and then a graph that's showing you the boom and bust cycles of each. So the blue is the hare, the red is the lynx. So kind of look at the pattern here. As the lynx population goes up, the hare population goes down. As a result of the hare population going down, the lynx population then goes down. So you can kind of see it's this back and forth. As the lynx population goes down, then the hare population is able to go back up. So as the hare population goes back up, eventually the lynx population is going to go back up. And all of this is showing you is how there's kind of this back and forth, like ebb and flow of population sizes that has to do with the cause and effects of predation. So that's called a boom and bust cycle. So it's kind of interesting. That's a predator-prey interaction called a boom and bust cycle. So email me if you're confused on that. And then the last thing I want to talk about just really quick, I think I'm going to actually finish this in the next couple of minutes, is human population growth. There's 2 configurations for stable human population growth. That would be a high birth and high death, or low birth and low death. That's what makes it most stable. When a certain demographic transitions from high birth, high death to low birth, low death, that's usually, you're going to see that when a third world or a less advanced country moves into being more advanced, basically. So you can see here countries, certain parts of Africa, what's labeled in the book for this, where you have a really high birth, high death rate, are going to be countries like or places in Africa, or places like Afghanistan. So continents like Africa and places like Afghanistan. Here you're going to see like the United States, where we have a little bit more, we have a higher birth rate than we do death rate, but it's a little bit more controlled, not like this one right here. And then here you have really no growth. Zero growth means that birth and death are equal. And so I discussed a little bit earlier why this one is pretty much ideal, although it's a little bit dangerous because you don't want to go into that negative growth. So the United States is actually in pretty good standing in terms of growth rate, because it's a very slow growth rate. All right, and then lastly, our global carrying capacity, and I'm sorry this is not updated. It's around something still like this. It's believed to be our current world population, I'm sorry, is believed to be somewhere around 7.345 billion at this point, and the estimated carrying capacity would be 10 to 15, question mark? Not sure. So while some believe we are still in exponential growth, at some point this is going to be reached, and we're going to have to do something about it unless nature takes care of that for us. Our ecological footprint, so the reason why the carrying capacity is believed to be at this point is what is happening with climate change and what we are actually doing to the earth, and what we can look at for ourselves, what we are doing to the earth that's going to determine what this carrying capacity will eventually be, is we can calculate our ecological footprint. So each individual person has an ecological footprint, which means on a daily basis or on a yearly basis, how much land and water are you actually consuming? So 1.7 hectares, I think, I'm going off of memory, that's a 100 by 100 meter plot of land. 100.7 hectare, so 1 hectare would be 100 by 100 meters, is sustainable, and the typical person in the United States is going to use 10. So we have a pretty big ecological footprint. And then what I would do in class is we would just have a discussion on what can we do to reduce our footprint. And I think everyone pretty much knows, instead of using paper plates, you can make sure that you use a regular plate and that you wash it so you're not throwing away a bunch of trash. You can walk instead, or ride a bike instead of driving. Carpool instead of each individual taking their own car. Just things like that. And then some would take it as far as stop eating meat, only eat vegetables, or become like a vegan. So anyway, that's how I would have ended that discussion. I went a little over 25, but I did finish it. Hopefully you got something from that, and you got a really good overview of what ecologists and environmental biologists and demographists are going to study. And hopefully for some of you that's an area of interest, because that's definitely a great career to go into. That is the end of our curriculum for AP Biology. I will send you the review material next week, day by day. Make sure that you get that HHMI done and get the Socrative done, and we will launch into test prep next week. All right, talk to you guys later.